Ayun, so kamusta naman kayo? So, hindi naman kayo binagyo? Sino sa inyong binaha yung bahay? Wala? So, lahat kayo safe? I mean, lahat kayo hindi na affected ng typhoon. Okay, buti naman.
Hello po, sir. Ang ano po, yun pong hindi po ata makaka-attend ngayon, ang ano po, ang medyo naapektuhan po talaga ng baha.
Okay. Nga pala.
Bali kami po sir, pero hindi naman po binaha. Bali ang problema lang po ay marami lang pong landslides po dun po sa amin. Tapos wala pong madaanan. Pag aalis po ay maglalakad po ganun.
Taga saan ka, sir?
Loklok po sir, Bawan po.
Oo, sa Bawan.
Bundok pa po. Apo.
Oo nga pala. Affected din ang Bawan.
Tapos dun po ay wala pa rin pong kuryente. Nag-move lang po ako sa dito po sa may Caltex po. Pumunta po muna ako sa mga tita para lang po makapagklase.
Okay. So, buong araw, online class kayo lahat? Or meron
Mm,
kayong...
Ngayon po sir ay online lang naman po.
Okay. Ito yung nakilabasa ko na yung status. So maraming walang kuryente. Yes. So hindi pa rin na okay. So ngayon wala pa rin kayong bubong. Taga saan si Ara? Ara May. Tanawan. Okay. So saan ka nagstay ngayon? Hmm. Okay, so habang nandito tayo sa online, so sulitin na natin yung time. So kailan yung next face to face natin, by the way? November 9? Tama? Yung next face to face natin, November 9?
Sir, November 10 po.
At 10, okay. So, November 10, pakipasa ng problem sets nyo ha. Para ma-checkan ko na. Okay, so how about your examination? So, have you answered all the questions? Okay, so, yeah, so you have to you have to exert extra effort for the finals. If you feel that didn't answer all the questions, so you have to double the effort for the final exam, double or triple. Yeah, because 50% of the grading system will come from the major exam. Okay, so we have to study harder and you have to uh, triple the effort. So with regards to the solution to the major exam, I will discuss it on our next face-to-face meeting. So for now, we will continue our discussion with convection heat transfer. So I'm sharing my screen. Okay, so we have this module. So our objective for today is to obtain an understanding of the physical mechanisms that underlie the convection heat transfer, to develop the means to perform convection transfer calculations, to model a boundary layer in convection heat transfer. Okay, so these first three objectives, we are already done with it. We will continue our discussion with performing dimensionless analysis and develop correlations for convection heat transfer with different fluids in laminar and turbulent flow. Today, we will discuss the Reynolds number, Prandtl, Nusselt number, Grashof number, and other important dimensionless parameters. So when we say dimensionless, there's no unit of measurement. So to differentiate force and pre-convection mechanism, so we already know what's the difference between the forced and free convection. When we say forced convection, so it uses a mechanism like pumps, blowers, compressors. When we say free convection, it takes place due to buoyant force as there is a difference in densities caused by the difference in temperature. So it's also known as the natural convection. So examples of natural convection are oceanic winds and uh, many more. So let's go first with dimensionless numbers. So we have here, first is the Reynolds number. So Reynolds number, so it gives a measure of the ratio of inertia and viscous forces in fluid flow. Excuse me. It is often used to determine if the flow is either laminar or turbulent. So in laminar flow, viscous forces dominate. So the flow paths are smooth, streamlined, and constant. Okay, so Reynolds number equals rho BL over uh, mu. So density times velocity times length all over the dynamic viscosity. So yeah, that's the Reynolds number. So when the value is less than 2000, the flow is laminar. When the value is greater than 4000, it is turbulent. So if it is in between, so it is called the transition flow. So this is for this reference only, but in other references, you will know that when in the other references it is 5 times 10 to the fifth. So when the value is 5 times 10 to the fifth below, so it's laminar, and then 5 times 10 to the fifth above is a turbulent flow. So yeah, it depends on the reference. It is still under discussion up to now. So that's for the Reynolds number. So so let's proceed with Nusselt number. So by the way, why are we studying this dimensionless uh, numbers? So the reason is that in our previous discussion, we do not actually solve for the heat transfer coefficient H. So because it's always given on the problem. However, in this more detailed discussion of the convection heat transfer, we are now dealing with solving for the value of H. So it is necessary that we know the dimensionless parameters because it will be the basis of our heat transfer coefficient. For example, Nusselt number. In order for us to solve for the Nusselt number, we have to determine the H. So if we know the value of Nusselt number, we can also determine the value of H. If we know the value of H, we can compute for the rate of heat transfer because the formula for the rate of heat transfer is the Newton's law of cooling formula, which is H or heat transfer coefficient multiplied by the area multiplied by the change in temperature. So that's why we are solving for the value of H now. Next dimensionless parameter is the Prandtl number. So the Prandtl number is the ratio of the kinematic viscosity to the thermal diffusivity. So it is used in many applications involving heat transfer in flowing fluids. So it gives a measure of the relative thickness of the thermal momentum boundary layers. So the formula for the Prandtl number is Cp times mu over K, where Cp is the fluid specific heat capacity, or simply specific heat. Mu is dynamic viscosity, and K is the thermal conductivity. So with regards to Prandtl number, so it can be solved and it can also be found on the table. I'm sharing my screen, or you can also relocate it on your mode table, the green book. For example, I'm sharing my screen. Mm, can you see the PDF now? Can you see the PDF now? The table 8.6, for example.
Yes po.
So you can see the Prandtl number here. It's already calculated. It's already on the table. So sometimes it's given on the tables. So we don't have to. solve for it. But in case we have to solve for the Prandtl number, just remember this equation. But this equation is also on your table, so that's good news because you don't have to memorize it. It's already on your green book. You can use it on the examination. So finally, the Grashof, not finally, but next is the Grashof. So the Grashof number, so it is used to determine the heat transfer coefficient under free convection conditions. So it is basically a ratio between the buoyancy forces and the viscous forces. Okay, when you look at your table, green book, you can find the formula also of the Grashof number. So it's on page, let me check. Okay, can you please help me find this formula? Grashof number. Yeah, I think I found it. Okay, so I think it's in the module. Wait, just wait. Can you uh, turn your module on page 63? Can you see it now? The Grashof number, the module in the module. So the Grashof number, so it is the ratio of the buoyancy forces to viscous forces. So in equation form, Grashof number equals G times beta times Ts minus T infinity times L cube over V squared. So G is, I think it's, what's the value of G? Is the gravity. Beta is equivalent to 1 over density multiplied by P over RT squared. So you have to, please refer to page 63 of your module. Okay, so yeah, that's Grashof number. So Grashof number is just usually used in a free convection. Okay, so yeah, that's Grashop. Let's move on to other numbers. So we have the Biot number, uh, Fourier number, Mach number, and Lewis number. So as time goes by, we will encounter these numbers as we solve for different examples here. Okay. So for your convenience, we also added the different uh, tables on the correlations. So as you can see on your green book, we have added different tables there about the correlations. So you don't have to memorize every formulas because it's already there in your table. Okay. So we have on your table we have the empirical correlations. We have the for laminar boundary layer or flat plate in parallel flow. We have that formula, flat plate in parallel flow. We have turbulent boundary layer, mixed boundary layer condition, empirical correlations due to Hilbert, average Nusselt number in turbulent boundary layer, the correlations due to Zukowskus. So yeah, to you just have to know which is the most applicable correlations to be used when solving a problem on convection heat transfer. Okay, so as you can see here on our screen, we have uh, also different correlations. So we have the summary of the forced convection heat transfer correlations for external flow. So we have different geometry. First is the flat plate laminar. So yeah, this is the uh, correlations. Flat plate liquid metal, flat plate turbulent flow. We have flat plate mixed flow cylinder. For cylinder, we have Kansen and Katz equation of average Nusselt number. You also have for spherical, falling drop, and packed bed of spheres. So that table is for forced convection heat transfer correlations. So we have heat transfer. Yeah, for flat plate. So I think I have discussed it yes last week. The formula that we should use for the flat plate is this one: H bar equals 1 over L multiplied by the integral of h dx. So the h bar means the average convection coefficient. So that's for the flat plate. For a circular plate, we have Nusselt number equals 0.023 RE raised to the zero point 0.8 PR raised to the N. So this is the equations that we will use if the flow is on a smooth pipe, turbulent flow on a smooth pipe. So R is Reynolds number, PR is Prandtl number. So you have to determine first the Reynolds number and the Prandtl number for you to be able to calculate for the Nusselt number. After you have calculated the Nusselt number, we can use it to determine the value of H or convection heat transfer coefficient. H equals Nusselt number over dk, because the formula for Nusselt number equals hd over k. So to solve for h, we have to rearrange the equation. So yeah, this, how about the PR raised to the n? So what should be the value of n? The value of n is either zero point 0.4 or zero point 0.3. For heating, we should use the value zero point 0.4, and for cooling, we have to use the value of zero point 0.3. Okay. Okay, so the equation is valid for fluids with Prandtl number PR ranging from zero point 0.6 to 100. So if above this value, if the value is not within this range, so we will use the value, this equation. Nusselt number equals 0.027 Reynolds number raised to the zero point 0.8 multiplied by the Prandtl number raised to the 1 over 3 multiplied by the ratio of uh, dynamic viscosity over dynamic viscosity. So to dynamic viscosity, the first one is uh, the dynamic viscosity of the fluid. The second one is evaluated at the wall surface temperature. Okay, so that's flow in a circular tube. So this table is the summary of the force convection correlations for internal flow. The table earlier is for external flow. So we have different correlations for external flow, meaning the flow outside, and the internal flow. So they have different values. So this is for internal flow. So don't worry, this is also in your table and module. So you don't have to memorize it. Okay. So yeah, for internal flow, we have this. This is the one that we have discussed, the Sider and Tate turbulent equation. So this is uh, applicable if your value of Prandtl number is in this range, zero point 0.7 greater than zero point 0.7 but less than 16,700. This one, the Nusselt number equals 0.023. This is the Dieter's-Polter equation. So turbulent, the condition is turbulent, fully developed. So the range of the Prandtl number is from zero point 0.6 to 160. Reynolds number is greater than 10,000. On the other hand, yeah, greater than or equal to 10,000. So same with this Sider and Tate turbulent equation. So we also have the Chiltern-Colborn analogy, Skupinski equation for liquid metals, Seban and Shimazaki equation for liquid metals. So we have different correlations. So I think this is an empirical formulas developed by the name, developed by the scientists on the name of the equation. Okay, so let's have some examples for you to be able to absorb what we are studying. Okay, so an air with a mass flow rate of 0.075 kilogram per second flows through a tube of diameter d equals 0.225 meters. The air enters at 100 degrees Celsius after a distance of L equals 5 meter, cools down to 70 degrees. So determine the heat rate coefficient of the air. The properties of air at 85 degrees Celsius are approximately Cp equals 1010 joule per kilogram Kelvin, K equals 0.03 watt per meter Kelvin. Dynamic viscosity is equivalent to 208 times 10 to the negative 7 Newton second per meter squared, and Prandtl number is 0.71. Okay, so this is an example of a fluid or air. A fluid in this problem is air, which is flowing through a tube or a circular cross section, circular cylinder or cylindrical. So for that, we will use this equation. Where's that? So this, as you can see, the problem is an example of a forced convection for internal flow. So this is what the table that we will use. So we will compute for the Nusselt number using the Dieter's-Bolter equation. So because why did we choose this equation? So we have to solve first for the uh, Reynolds number for us to be able to know if it is a turbulent or laminar. So let's solve first for the Reynolds number. Then after solving for the Reynolds number, if we found it turbulent, so we will use this equation for the Nusselt number. So because we are given the Reynolds number and Prandtl number, so the correlations that will flow should be related to that. And the perfect one is this Dieter's-Bolter equation. So yeah, let's check first if it is a turbulent flow. And let's solve for the value of Prandtl number. and Reynolds number. So if the value of the turbulent of the Prandtl number is within this range, as well as the Reynolds number, so we will use this equation. Nusselt number equals 0.023. Reynolds number raised to the zero point 0.8 over Prandtl number raised to the n. Okay, so going back, let's solve for the Reynolds number. So we are given the mass flow rate instead of a velocity. So we have to use this equation. Reynolds number equals 4m over pi d times dynamic viscosity. Okay, so uh, mass flow rate is given, which is 0.075. D is the diameter. And where did this number came from? 208 times 10 to the negative 7. Okay, so it is from the table. So what temperature will you use if the given is 170? So let's read the sentence. Air with mass flow rate of 0.075 kilogram per second flows through a tube of diameter d equals 0.225 meters. So the air enters at 100 degrees Celsius and after a distance of L equals 5 meter, cools down to 70 degrees Celsius. So there is a change in the temperature from 100 to 70. So for us to be able to determine that what temperature to be used, we have to use the average temperature. What is the average temperature of 170? So that should be 85. So this value, 208 times 10 to the negative 7, Cp of 1010, and conductivity of 0.03 is based on the value on the properties of air at 85 degrees Celsius. So you have to get the average temperature. Okay? Okay. So yeah, we have to solve for the Reynolds number first. Okay. Okay, so yeah, the Reynolds number is 20,400. So we have to use this equation for m over pi d times dynamic viscosity. So these values came from 85 degrees Celsius. So Now we have the Reynolds number, which is 20,400. So do you think it's a turbulent or a laminar flow? So it's a turbulent flow. So with regards to that, so let's go to the table for correlations for internal flow. So this is a turbulent flow fully developed with the Reynolds number of greater than 12 and 10,000. So the value that we have calculated is 12,000. So this is within this range. How about the Prandtl number? So we have to calculate the Prandtl number. So Prandtl number, it's already given. So you don't have to calculate it na. So it's given on the table, which is 0.71. So the Prandtl number is 0.71. Going back, so is it within the range? Yes, 0.71 is still here. So yeah, we have to use this Dieter's-Bolter equation. So to solve for the Nusselt number is Hd over K is equal to 0.023 Re raised to the zero point 0.8 Pr raised to the zero point 0.3. So why zero point 0.3? As I have said, zero point 0.3 is used for cooling. So in this case, air enters at 100 and after a distance of 5 meters, it cools down to 70. So it means that the purpose of this heat transfer is for cooling. Okay, so if it's for cooling, it should be zero point 0.3. If it's for heating, it should be zero point 0.4. So that's why it is now zero point 0.3. Substituting the numerical values, we have 0.023 times Re, which is 20,400, raised to the zero point 0.8 multiplied by 0.71 raised to the zero point 0.3 is equivalent to 58, equals 58. Okay, so H equals K over D times Nusselt number equals 0.03. Yung K natin is on the table of properties. 0.03 over, this is given 0.225 multiplied by the Nusselt number, which is 58. So we will arrive at 7.73 watt per square meter Kelvin. So that is the value of H. Questions? Do you have any questions? No questions? So let's move on to next example. So for this one, you have to solve on your own. Uh, okay, air at 1 atmosphere and 300 degrees Celsius is cooled as it flows the velocity of 5 meters per second through a tube with a diameter of 2.54 centimeter. Calculate the heat transfer coefficient if a constant heat flux condition is maintained at the wall and the wall temperature is 20 degrees Celsius. above the temperature along the entire length of the tube. So we have air at 1 atmosphere. 1 atmosphere is equivalent to 101.325 101.325 no 1.0132 Pascal. 1.0132 times 10 to the fifth Pascal and 101.325 kilopascal. So yeah, that's the 1 atmosphere. Okay. So in this case, it also flows through a cylindrical configuration geometry, cylindrical geometry, or the specifically the tube. So the air is cooled as it flows through a tube with a velocity of 5 meters per second. So what we have to do is to calculate the heat transfer coefficient H. So heat flux condition is maintained at the wall and the wall temperature is 20 degrees above the temperature along the entire length of the tube. So, okay, so the density is first calculated using the ideal gas law in order to obtain Reynolds number. Apply the appropriate value of R for on a mass basis. Air of R for air in a mass basis. In this case, to compute for the density, we have to use the ideal gas law. Do you still remember the ideal gas law on your thermodynamics? Yeah, so we have to use that again. Density equals P over RT. As I have said, pressure is 1 atmosphere and equivalent to 1.0132 times 10 to the fifth Pascal. So over what's R? Rydberg constant ba yung R? So the unit of R is joule per kilogram Kelvin. So we have R for air is 287 joule per kilogram Kelvin multiplied by the temperature of 300 plus 273 to make it a Kelvin. So the density that we will compute that we computed is 0.6161 kilogram per cubic meter. So you have to double check the units of measurement. So we have here the Pascal, Kelvin, and Joule per kilogram Kelvin. So what will remain will be kilogram per cubic meter. Should be kilogram per cubic meter. And that's your density. Okay, so the following data is obtained assuming air to have the properties of nitrogen. Okay, so this is the value of the properties in appendix. So we have Prandtl number is 0.713, dynamic viscosity is 1.784, and K is 0.0262 watt per meter Kelvin. Cp is 1041. Can you check if this value is correct on the table? So our fluid here is air. And then the temperature that you will use is 300 degrees Celsius. Okay, so you have to interpolate. No, I think no, not interpolate. Okay, so this is based on the properties of air. So compute for the Reynolds number. So Reynolds number is diameter times velocity times density over dynamic viscosity. So we have diameter of 2.54 centimeter, velocity of 5 meter per second. So this one is 5, diameter is 2.54, and use the value of density. Yung na-compute natin, our computed value is 0.6161 kilogram per meter cube over dynamic viscosity of 1.784 times 10 to the negative 5. So we will achieve the value of 4,386. 4386. Okay, 4,386 yung value ng Reynolds number. So, with that being said, so may reference tayo na nagsasabi na 4,386 is already turbulent flow. So, we will use again this equation, Nusselt number equals hd over k equals 0.023 Re raised to the 0.8 multiplied by the Prandtl number raised to the 0.3. Again, 0.3 because it is for cooling purpose. So we will achieve the value of 17.03 for the Nusselt number. So please double check if the value is correct. 17.03. Okay. So if we already have the value of Nusselt number, we can now get the value of H, which is we are just rearranging this equation. H equals K over D multiplied by the Nusselt number. The value of K is 0.262, D is 2.54 cm, and the computed Nusselt number is 17.03. So therefore, we will get this value 17.57 watt per square meter Kelvin. Question? Do you have any question? How do we come up with this value? So if we already know the value of H, we can now solve for the rate of heat transfer using the Newton's law of cooling, which is HA delta T. Question? No question? Did you understand what we have just solved? Okay, if you don't have any question, we can move forward with the next example. Let's look for another example. Mm, okay, this one. Water flows with an average velocity of 0.355 meter per second through a long copper tube. Inside diameter equals 2.2 centimeter in a heat exchanger. The water is heated by steam condensing at 150 degrees on the outside of the tube. Water enters at 15 degrees Celsius and leaves at 60 degrees Celsius. Determine the heat transfer coefficient H for the water. So please solve this first and then we will discuss it after 5 minutes. I already provided the first step. So we have to evaluate the average bulk temperature of the water, which is 15 plus 60. So water enters at 15 degrees and leaves at 60 degrees. So the water is heated, the water enters at 15 and leaves at 60. So there's a heating that occurs. So determine the heat transfer coefficient H for the water. So how will we determine the heat transfer coefficient H if we do not know the temperature to be used? We have two temperature, 15 and 60. So we need to get the average temperature. We have to evaluate the average bulk temperature of the water, which is 15 plus 60 over 2. It is 35. So in this temperature, we will get the water properties from the table. So at 37.5, the density is 993 kilogram per cubic meter. The dynamic viscosity is 0.000683. Cp is 4.17 times 10 to the third power joule per kilogram Kelvin, and K is 0.63. So that values are from the table. Okay, so please solve on your seat and then we will discuss it after 5 minutes. Okay, so let's discuss the solution. Let's continue. So we have here, we determine these properties based on the temperature of 37.5. So this is for inside temperature. Okay. So to calculate the Reynolds and Prandtl number for the flowing water, we have to use the formula that I have told you. For the Reynolds number, you have to use d times velocity times the density. D is diameter, V is velocity, and this rho is for density over dynamic viscosity. This is given diameter 2.2 centimeter. Velocity is also given 0.355 as well as the density. So this is 993 over dynamic viscosity of 6.83 times 10 to the negative 4. So this one. Okay. So is equivalent to 11,350. So this is a turbulent flow inside. With regards to Prandtl number, so we have here Cp or specific heat over times dynamic viscosity, which is 4.17 over the thermal conductivity K. So that is 4170 times 6.83 times 10 to the negative 4 over 0.63 equals 4.53. So Prandtl number is 4.53 and Reynolds number is 11,350. So we will use this equation. So the flow is turbulent, and since the tube is long, one may use the Sider-Tate turbulent relation. Why we should use this equation? So because of the temperature difference, as you can see on the problem, the water is heated at by the steam condensing at 150 degrees Celsius on the outside of the tube, while the inside of the tube is 15 degrees and lives at 60. So there is a great large significant difference on the temperature. So we have to use this equation. So looking at this on the table, so as you can see the description for this equation, Sider and Tate turbulent equation. So turbulent fully developed Prandtl number is zero point 0.7 up to 16,000. So we are within this range. Reynolds number is also above 10,000. And there is a large change in fluid properties between the wall of the tube and the bulk flow. So yeah, it is the temperature of the wall is at the wall is external flow is 150 while the inside the tube the bulk flow is only 37.5. So we have to use this equation correlation because of the large change in fluid properties. Okay? So remember this equation, large change in fluid properties. So going back to the problem, so we already have this 37.5. So for this is for internal flow. For external flow, we have to evaluate the average temperature from 37.5 to 150. So the average of 37.5 and 150 is 93.75. So 150 plus 37.5 divide 2. The answer is 93.75. So at this temperature, you have to look for the value of the uh, fluid at 93.75. So water. You have to the fluid is the water. So you have to determine the properties of water at 93.75. So you need to determine the value of UW. So with regards to we already calculated it, or we already found it as 0.000683. So this is based on 37.5. The UW is based on 93.75. See the average of 37.5 and 150. Okay? So the value is 306. So substituting the numerical values of H D over K equals 0.027 RE. Okay, so you have to substitute the value of RE, PR, and U. So RE is 11,350. Prandtl is 4.53. So, and then U is 0.00683. And U of water for external is 0.00306. So we have two values of U raised to the 0.14. So we will get the value of H as 2498.1 watt per square meter Kelvin. Yeah, did you get it? Is it clear? Is the solution clear? Okay. So why did we use the 93.75 average? So because of the uh, because we have to evaluate the average bulk temperature of the water. So outside flow is I mean temperature of the outside, which is 150, and the inside of 37.5. So the average temperature is 93.75. So from this temperature, you will get the value of the dynamic viscosity of the water at 93.75 degrees Celsius. So yeah, we already have this U and UW. We also have the Prandtl number and Reynolds number. So we have the diameter and the K. You also have the Nusselt number. This is the formula for the Nusselt number. Yeah, this 0.027. So Nusselt number is HD over K. So we can solve now for the H. Okay. H is equivalent to Nusselt number times K over D. Okay. So yeah, that's our way of solving. So in for your reference, I included the summary procedure for all the convection problems. So first, specify the fluid. So specific geometry. Next, we have to specify the geometry. So if it is a flat plate, we have a separate correlation for that. If it's exterior interior flow, we also have a separate correlation for that. So next, free or forced convection. So it depends on the problem. What we are solving now is a forced convection because of we use as our mechanism or the bulk fluid motion for the bulk fluid motion. So we are using the forced convection now. So with regards when we are discussing the free convection, we will use another correlations. We have the Grashof number for the free convection, so we will encounter that later. Okay, after specifying the if it is free or forced convection, we have to determine the temperature for fluid property determinations. In our recent example, we get the average bulk temperature. So we get the average of the inlet and the outlet temperatures. So the average will be the basis of the fluid property determination. So yeah, we have if we already get the properties, we gonna evaluate for the Reynolds number for force convection to determine the flow regime. Also, if it's a pre-convection, we have to determine the Grashoff's and Prandtl number. So if we already identify it, we can now use the select correlation for convection heat transfer coefficient. For example, when we found out that the Reynolds number is for turbulent, we can use the table for turbulent flow. If we found out that it is laminar, we can use the table for laminar flow. So select correlation for convection heat transfer coefficient, and then modify temperature property determination as needed. Calculate the heat transfer coefficient. We can now calculate for heat transfer coefficient using the table of correlations. For example, in the we determined that the Reynolds number is a turbulent flow. So we have to, and also there is a large change in fluid properties. So we will use this equation for the Nusselt number. When we already solve for the Nusselt number, we can solve now for the value of the heat transfer coefficient. Because the formula of Nusselt number is Hd over K, we can now solve for the H or calculate heat transfer coefficient. Once we calculated the heat transfer coefficient, we can now proceed with calculating the heat transfer rate. So we have HA delta T for exterior flows and for internal flows. So that's our summary of procedures for calculating the convection coefficient of heat transfer H and also the heat transfer rate itself. Do you have any question on the summary procedure? Okay, so if you don't have any question, we have here additional practice problems. So we can solve for these problems. This is applicable for heat transfer coefficients. Solving for heat transfer coefficients, we have boundary layer transition and dimensionless parameters. So please solve these practice problems. I will also give you another sets for you to be able to have more practice and solve these problems. Because the secret of passing this course is the uh, familiarity with the equations, familiarity with the procedures on how to calculate the required parameters, required properties. So we cannot uh, we cannot solve the future problems if we do not have the mastery of the uh, equations. So you don't have to memorize the equations, but you have d- to determine which should be applicable on the problem. You have so many correlations, and the only way to solve it correctly, the only way to solve the problem correctly is to have uh, mastery of the equations and correlations and its applications with regards to different geometry and conditions. So yeah, you have to practice. That's the secret for uh, understanding the lesson. Practice problem solving. So next week we will continue discussing the convection heat transfer, and eventually we will proceed with heat exchanger topic. So please submit also your problem sets on November 10 during our face-to-face discussion. With regards to your midterm exam, I will try to finish checking. Hopefully, many of you will pass the exam, and the result will be on. I'll try it to be. I'll try it to finish on November 10, and then I will distribute to you. Do you have any more questions? Yes, Alvin Anthony.
Sir, excuse po. About po sa PPT, kailan po kaya siya maa-upload?
Yeah, I will upload it today, within today. This presentation will be uploaded within today.
Tapos po, sir, sabi niyo po kanina ay by next week po, ay may klase po may schedule pa po tayo bukas. Ano po yun? Magka-class pa po tayo bukas.
Yes, we will continue our discussion tomorrow on convection heat transfer. And maybe next week we will proceed with heat exchanger. And then after heat exchanger will be the radiation. And after radiation is multi-mode heat transfer. And then after multi-mode heat transfer will be your presentation of technical report wherein you will apply your knowledge on simulations using the software that I have introduced to you, the ANSYS software. So for those who haven't tried to use the software, please do because you will need it on your technical report. Okay, so let's see each other again tomorrow, online class again. Thank you.
Thank you po, sir.
Thank you po, sir.